Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallics in catalysis and biology. We have been talking about olefin metathesis, particularly catalyst development aspects in the last few lectures, and we had focused on alkene metathesis to begin with. And what we had seen in the last few lectures that both sterics and electronics they play a powerful role in modulating in the catalyst activity, particularly in making catalyst more efficient in their catalytic processes. So, in that regard we had seen how putting more bulky ligands on the metal help facilitated better activity for Grubbs catalyst by allowing phosphine dissociation, and further incorporation of very good sigma donating ligands on the metal facilitated olefin binding, which both together help facilitated this metathesis reaction. So, this quite a bit of rich organometallic chemistry, particularly with regard to the metal ligand binding as well as metal ligand pi back donation, all of those interaction played a crucial role in the evolution of olefin metathesis catalyst, which went on to become better with the discovery of second generation catalyst as opposed to the Grubbs first generation catalyst. We had also discussed about Harman's work on the comparison of Grubbs first generation and second generation catalyst in the ring opening metathesis polymerization of cyclooctane, and that definitely proved that indeed the second generation catalyst bearing N-heterocyclic carbenes were more superior in terms of fastness to produce the product than the corresponding Grubbs first generation catalyst. So, with this behind us, today we are going to sort of look at the key points of this metathesis catalyst as we proceed in today's lecture, and these are particularly with respect to alkene metathesis that we are talking about. So, this metal carbene moiety acts as the active center in catalyst. Catalysis. Second thing, that of the various metals which could stabilize metal carbene moiety, the metals of choice for metathesis reactions were molybdenum, tungsten, rhenium and ruthenium. And ruthenium are the metal of choice. For metathesis reaction. And you know, the earlier times the catalysts were derived from transition metal halide, as is shown over here, and carbon ion donors. tungsten hexachloride plus dimethyl aluminum chloride would give tungsten tetrachloro dimethyl, that in presence of ethanol would eliminate water to give tungsten oxo dichloride with this intermediate transition state giving Cl W Cl oxo carbene plus methane. So, this is another way of generating the tungsten oxo carbene complexes. Now, in this regard we should mention that some of the earlier molybdenum version that we had seen were of molybdenum imidocarbene of similar or related formulation. So, the way this particular complex which was prepared from the halide and this dimethyl aluminum chloride resulting in the tungsten oxo carbonyl complex. So, along the same line the Schrock had synthesized the corresponding imidocarbene complex as is shown over here. Schrock's complex was synthesized much later in 1990 and this is imidamolybdenum complex methyl CF3. So, this is a very complicated complex which has both imido and the carbene complex and also has this CF3 methyl moieties CF3 methyl moieties around the alkoxides. So, this is kind of a complex, however, this was found to be highly active catalyst but poor functional group tolerant, but poor then the next important thing is while increasing the electron withdrawing nature of R, the catalytic activity increases, the catalytic activity increased with increasing electron withdrawing nature of R, and this can be seen why these CF3 groups were put in place. Another important feature of this complex is the sterically demanding olefins, even the sterically demanding olefin tri and tetra substituted tri and tetra substituted olefins can undergo metathesis. So, this is a very interesting development where this molybdenum imido carbene as prepared by Schrock went on to become an extremely high active catalyst. Then the catalytic activity could be increased by putting electron withdrawing groups, and also can be, because of higher activity, it can be used for slow reacting tri and tetra substituted olefins. The only drawback to this highly active molybdenum catalyst is that they are not very functional group tolerant, or that the catalyst could easily be poisoned by different functional groups in the olefin. So, these are supposed to be the limitation of these catalyst, molybdenum catalyst. Now, we had seen this tungsten oxo carbene complex which was synthesized from tungsten hexahalide. Then we have seen Schrock's molybdenum imido carbene complex, and now we are going to go and look at Grubb's phosphine carbene complex. Grubb's complex, and this was synthesized much later, 1995, about 5 years later than that of the Schrock's which was synthesized in 1990. And this angle between these two halide was 167 degrees. Now, the main feature of this ruthenium compound is that these are functional group tolerant, tolerant like, and it could tolerate groups like CO, OH, NH2 amido, and that the catalyst would not get poisoned by the presence of this group in the olefin, and hence this was supposedly a very big attribute for this ruthenium carbene complex. And then the other important features included selectivity towards sterically unhindered olefins and strained olefins, and the third thing is the tri and tetra substituted olefins cannot undergo metathesis. Tri and tetra substituted olefins did not undergo metathesis. So, the point to note is the following. Now, when one compares Grubb's complex with that of the Strock's complex as discussed earlier, one major difference is that this is exactly opposite to that of the Grubb's complex in terms of being functional group tolerant. Whereas Grubb's compound which was molybdenum was highly reactive towards functional group and intolerant, and hence the catalyst would get poisoned in presence of various functional group like CO, OH and H2, whereas the Grubb's ruthenium complex is exactly the opposite, and that it does not get affected by the presence of other functional group, and hence the catalyst would survive the presence of other functionality and would effectively carry out the catalysis. Other important difference is that the Strock's catalyst being highly reactive could carry out metathesis of tri and tetra substituted olefins, whereas the Grubb's one is exactly the opposite, and it did not facilitate or did not allow the metathesis reactions with tri and tetra substituted olefins. So, and third thing, the third difference is obviously the ruthenium carbene is more air stable, whereas the Strock's molybdenum carbene is more sensitive to air and moisture. Lastly, the fourth difference is that ruthenium carbene has only one kind of multiple bond between ruthenium and carbonic moiety, whereas the Strock's complex had two kind of multiple bonding, one between molybdenum and carbene and the other between molybdenum and imido moiety. Another interesting thing is that even though they are completely complementary to each other, together they have made a very good set of catalyst combination where every type of metathesis reactions could be facilitated. Now, one important thing, as I was talking about, this coordinative and electronic saturation and unsaturation is a very important factor in guiding catalyst activity, and in this regard both the Strock and Grubb's catalyst have a low coordination number and these primarily we had discussed by arising from phosphine dissociation in Grubb's catalyst low coordination number. This is very important in order to facilitate alkene attack on central metal atom, or this is called alkene binding. So, the point to note is this low coordination number very is important for alkene binding, and that has been achieved by phosphine dissociation in presence of Grubb's catalyst. And another advantage of olefin metathesis reaction is the fact that olefin metathesis can be carried out both under homogeneous conditions as well as heterogeneous catalysis conditions, and as preferred by industry, most of the industrial processes utilizes heterogeneous catalyst till date. Industrial processes utilizes heterogeneous catalyst. Whereas the laboratory applications often, however, implies homogeneous catalyst. Homogeneous catalysts are mostly used in laboratory applications. And towards this development, a lot of different kinds of catalyst using ruthenium, molybdenum and other metals were synthesized, and as we had seen that the activity of Grubbs catalyst was improved by replacing phosphines with NHCs and so on and so forth, and several types of or several variants of Grubbs catalyst were developed, and they were later characterized as first generation and second generation type of catalyst. And in this regard, the notable few catalysts which are by far the best in terms of the activity are shown over here. The variants of Grubbs catalyst that are that show great activity. To start with is this is the first Grubbs catalyst. Then came the carbene substituted Grubbs catalyst. Followed by the imidazole based Grubbs catalyst, followed by the bis carbene based Grubbs catalyst. So, what we see over here is that a significant improvement of Grubbs catalyst happens as phosphines get replaced by NHCs to becoming that with 2 NHCs, where both phosphines have been replaced with NHCs and the activity keeps getting better. So, with this we come to the conclusion of today's lecture, in which we have looked into various types of catalysts that have been developed, starting with the tungsten based carbene complexes, to that of molybdenum, to that of ruthenium. And what we saw, that between Strock's molybdenum and Grubbs ruthenium catalyst, there is the presence of complementarity in terms of the Strock's molybdenum catalyst being extremely sensitive to air and moisture, whereas Grubbs ruthenium catalyst is stable to air and moisture. Strock's molybdenum catalyst is highly reactive and hence functional group intolerant, whereas Grubbs ruthenium catalyst is functional group tolerant. Strock's molybdenum catalyst is good for the reactions of tri and tetrasubstituted bulky olefinic substrates, whereas the Grubbs ruthenium catalyst extremely actually does not undergo any reaction with the sterically demanding tri and tetra substituted olefins. So, there exists a huge complementarity between these two catalysts, but the end the appreciation for metathesis reaction is more possible because of the synthesis of Grubbs catalyst, which is sort of virtually took out this air sensitive metathesis chemistry out of the glove box to be able to successfully practiced in open air. Now, one thing which is important over here, that for this metathesis reaction olefin binding is a crucial step, and that is facilitated by a low coordination number of the catalyst, and this is achieved by phosphine dissociation, giving rise to low coordinated metal species for both Strock and Grubbs catalyst, which can then finally bind olefin, giving metathesis reaction. So, apart from this, industrial processes prefer heterogeneous catalyst, whereas homogeneous catalysts are still preferred under laboratory applications reactions. With this we will conclude this our discussion on olefin metathesis reaction, and we are going to alkene metathesis reaction, and we are going to take up cross metathesis, another variant of olefin metathesis reaction in more detail when we meet in the next class. Till then, goodbye and thank you.